Alright, good morning everybody. We're going to be taking a look at simplifying radical expressions. And these guys are your square root problems. So we have this property that we want to use. It's called the product property of square roots. It says this: if you have any number a times any number b, that is the same thing as the square root of that number times the square root of the second number. Okay? Now let's do a quick example of that. Say I had the square root of 4 times 25, then that is the square root of 4 times the square root of 25, which is 2 times 5, which is 10, which is to be expected, right? Because we know that 4 times 25 is the same thing as the square root of 100, which is also 10. They're equal to the same thing, so through transitive property they must be equal to each other also. Now let's apply this to simplifying a square root problem. So say I have something that is not a perfect square, like 100, because that's like living the dream there. What if I'm not living the dream and I've got the square root of 12? Well, the product property of square root says this is really the same thing as the square root of 4 times the square root of 3. Well, how did I get to this? Well, I'm just going to use a prime. I'm going to do the prime factorization here. And the numbers on the end of my factor tree are my prime factors. And I know that one of them is 3, and since I have a pair of 2's, I'm going to rewrite that as 4. Now I can go through and simplify the square roots that are perfect squares, like this 4 here. Well, I know that's 2. We don't have to put the dot when we're doing multiplication. It's implied that when the number in front of the square root is just multiplied together. So, wrong way. This guy simplifies into the square root of 12 is equal to the square root of 4 times the square root of 3. Square root of 4 is 2 times radical 3. Okay? Now let's take a look at another one. So imagine I had this guy right here. This radical 90, or the square root of 90. Well, 90 is 9 times 10. I'm not going to factor that any further because I found my perfect square there. And I'm going to rewrite this as the square root of 9 times radical 10. Now, this guy is going to be able to be simplified, but this guy right here is stuck. So I'm going to just rewrite this one as 3 radical 10. Okay? Hopefully you'll get a little bit of practice with those and they'll become clear to you. Now, if that's all there was to it, this would be like the easiest topic of all time. But imagine I have something like this, and it might just say, find radical 3 times radical 15. And they don't mean like point at it, like it's right there. They mean simplify this guy. So radical 3 times radical 15 is the same thing as the square root of 3 times 15, which is really radical 45. Now the prime factorization of 45 is 9 times 5. So I'm going to rewrite this guy as radical 9 times radical 5. Once again, this one will be able to simplify, and this little guy right here is not going to market. We can rewrite this as 3 radical 5. Wonder if that's always going to work, right? Well, what happens when I start introducing variables into the mix? So imagine I have something that's a little bit more complicated. So say I have 40 x to the 4th, y to the 5th, z cubed underneath the radical. Now it's getting to be a little bit more complicated. So I can prime factorization 40 as best I can. I think that's 4 times 10. I know from my last problem that 10 is a stopping point, so I think this is going to be something like 4 times 10. Now, x to the fourth could be rewritten also, right? This guy is really kind of like, well, let's just leave it like that. X to the fourth. But y to the fifth, I'm going to rewrite that as y times y to the fourth. And I'll show you why in a second here. And this z to the third, I'm going to write that as z times z squared. Now, just like any number, like any perfect square, 4 is 2 times 2. I'm going to use the same type of reasoning that x to the fourth, it jumped the gun there, x to the fourth is like x squared times x squared, right? Because we know that x squared times x squared is equal to x to the second plus 2 plus 2. So they're the same thing, right? And when we have something multiplied by itself, well, that literally is how you find the square root. So this x to the fourth should be able to come out as an x squared. Okay? Now, the ones that are going to come out, I'm just going to underline them in green here, are this one, and this one. Underneath the radicand here, we have the 10, one y will stay behind, and one z will stay behind. Let's see how this is going to play out. All of this equals, well, the 4 comes out as a 2 times the x fourth comes out as an x squared. I'm done with you. And this y to the fourth comes out as a y squared. We put our radical sign, and then we write whatever's left behind. There was a 10 left behind, a y left behind, and a z left behind. And now we're totally simplified. We can't do anything else with this expression. Alright, should we take a look at another one? Okay, sure, no problem. Now, we know that most of the math operations have like a pair. So in multiplication, pairs up very nicely with division, right? And so we're going to have to take a look at how these square root problems work with division. We call this rationalizing the denominator. Just like we're not allowed to have negative square roots in our simplified answers, we don't allow square roots in the denominator of our fractions. So imagine I have one that looks like this. Let me show you what that means. Example. Radical 10 over radical 3. Now, neither of these can be simplified because, you know, well, we've done 10, the cup keeps popping up, and that guy is just, you know, doesn't have any perfect squares in it, and 3 doesn't. So what's the big deal? We should be done, right? No. We've got a square root down here, so we need to get rid of this guy. To do that, we're going to use our old friend multiply by fancy 1. And in this case, I'm going to let 1 equal the square root of 3 over the square root of 3. I'm choosing the denominator over itself to multiply to get rid of this thing. Now, the product property of square roots is going to let me multiply these two together and multiply these two together. So this looks like, well, that's the square root of 10 times 3 over the square root of 3 times 3. Hey, that's a 9. So that's going to just come out as 3 because the square root of 9 is 3. The top is 30. And I don't imagine any perfect squares because it's a 3 and a 10, so that's good. Now we are going to check, do we have any square roots left in the bottom? Nope. And this guy, it cannot be simplified. Then we are completely simplified at this point. Now, imagine that things don't work out so perfectly, because that was a nice little neat example. Our next example is going to try to rationalize the denominator again, but watch what happens. We have the square root of 2 over radical 6. Well, I'm going to multiply by fancy 1 again. That's radical 6 over radical 6. And that is the square root of 12 over, hey, square root of 36. I'm just going to write a 6 right here. But wait a second. 12 is really equal to 3 times 4. And I think 4 is a perfect square. So let's see what happens here. That is the square root of 4 times the square root of 3 all over 6, which is 2 radical 3 over 6. Now look, we've got this fraction that can simplify. 2 goes into 2 one time and 2 goes into 6 3 times. Well, that gives us radical 3 over 3. So, when you start simplifying these bad boys, sometimes they just keep taking you down the rabbit hole, and you have to just keep simplifying and simplifying until you end up with an expression that is no square roots in the bottom, and the numerator can't be simplified either. Okay, now if that was all there was to it, then we would be really happy. Let me show you the most complicated thing that can happen here. This is called using a conjugate to rationalize a denominator. That's a lot of words. Okay, so this is using a conjugate to rationalize a denominator. Almost didn't even fit on the whole line there. Did it squeeze that in there? Yeah, okay. Here we go. Yeah, they look like this. 2 over 6 minus the square root of 3. Oh, great. We've got a radical on the bottom, but it's attached to this 6. Now, if I try to multiply by square root of 3 on the bottom, then the square root of 3 is basically just going to pop over onto the 6 and be gone on this side. So that's not going to work. If you don't believe me, you can try it out, or I'll show you on Tuesday. The trick of these types of problems is to use a conjugate. Conjugate is you take this denominator and you make this sign the opposite. And you use that as your fancy one. So 6 minus radical 3's conjugate is 6 plus radical 3 over 6 plus radical 3. Holy moly, it just got more complicated. That's alright. Distributive property says that 2 times 6 plus radical 3 over 6 minus radical 3 times the quantity 6 plus radical 3. You're like, hold on a second, Mr. Cooper. It doesn't look like you're going anywhere. You're making it worse. But through a little bit of algebra here, we're going to end up with something better. I'll just do the top. That's easy. 2 times 6 is 12, plus 2 times a radical 3 is 2 radical 3. The bottom one, I need to FOIL this guy out, or distribute. This times everything in there, and then this piece times everything in there. I'll do the first 6, and then I'll do that negative radical 3 second. 6 times 6 is 36. 6 times a positive radical 3 is plus 6 radical 3. Negative radical 3 times 6 is a negative 6 radical 3 times a negative times a positive is a negative. Radical 3 times a radical 3 is radical 9. Okay, whew. Looks terrible. But here we go. Now the magic happens. On the numerator we have 12 plus 2 radical 3. In the denominator we have 36. And look at this. A positive 6 radical 3 cancels out with a negative 6 radical 3. And then subtracting the square root of 9, which is 3. And last step, 12. Let's just carry down this numerator. And then we'll subtract here. And voila, it worked. There's no more square root in the bottom, and all the square roots in the numerator are simplified, and there's no common bases or anything, so those are all done. Okay, well, hopefully that made sense to you. If not, do your best. Watch the video again if you need to, and good luck for today.